No, it is on. Okay, good.
All right, good morning, everyone. Well, we've made it to halfway. 2 weeks down, 2 weeks to go. Task is long, but glorious. So Igor Klebanov, one of the two scientific organizers, is gone. He was here the first 2 weeks. Miriam Svedich, who is your other scientific organizer, will be here later today. And in the meantime, we're continuing with Silviu Pufu, telling us about CFT in more than 2 dimensions.
All right. I should say again that more than 2 dimensions for this lecture series means 3 dimensions, one at a time. And just a brief review of what I ended with on Friday. So I started explaining how to construct explicit conformal field theories in 3 dimensions. One example, so that means with Lagrangian descriptions. One example is free theories of scalars or fermions. These are conformal in any number of dimensions, not just in 3 dimensions. But then in 3 dimensions, we can make the scalars and the fermions interact. And it's believed in many situations that in the infrared, the theory flows to a non-trivial conformal field theory. One example of that is the ON vector model, where we start with n scalars. So I goes from 1 to n. These are real scalars. And we have a kinetic term, we have a mass term, and we have a quartic interaction between the scalars. And if we tune the mass appropriately in the infrared, we can reach a conformal field theory. And that conformal field theory, that's a critical ON vector model. And it's solvable in the large n limit. It becomes almost free. In particular, the scaling dimensions of the scalar fields are 1/2 the free scaling dimensions plus order 1 over n corrections. But it's not quite, that doesn't work for all the operators. For the ON singlets, they acquire a order 1 anomalous dimension. Phi I in the free theory has dimension 1, because each scalar has dimension 1/2. But the critical point, it has dimension 2. And my understanding is that Igor explained how that happens in these theories using a Hubbard-Stanovich trick, and phi I corresponds to the Hubbard-Stanovich field. Okay. Another example is we start with n Majorana fermions. So again, I goes from 1 to n, and we can also have Majorana fermions in a scalar field. And we can have a mass term for the scalar field, quartic interaction, and also a Yukawa term such that we make the scalar field interact with the fermions. And it's also believed that if we tune m squared in the infrared, we flow to a non-trivial conformal field theory. It's again almost like the free theory. So for instance, at large n, psi I has dimension 1. That's the free dimension of a fermion in 3 dimensions. But doesn't work for all the operators again. For instance, for this scalar field phi in the UV has dimension 1/2, but in the infrared has dimension 1. Okay, so you can think of this Lagrangian here as an RG flow between a free theory and some interacting CFT, and same here. You can think of it as an RG flow between a free theory, the free theory of n fermions and 1 scalar, and some interacting theory. What's interesting about it? Well, so both of these theories have ON global symmetry. The scalars have ON symmetry because they're real, and so do the fermions if they're Majorana fermions in 3 dimensions. And one thing that's interesting about this theory is that so suppose we are at the conformal fixed point, so that means we tuned m squared, but now we don't want to tune m squared anymore, so we turn on we change m squared by a little bit. Then what happens at low energies is that this scalar field becomes massive, so we can forget about it. And what we obtain is a theory of free fermions. So the RG flow for this theory is the other way around in some sense compared to this one. This one flows from n free scalars to some interacting theory. But this one, suppose we start with the interacting theory, and then if we turn on this deformation, we can flow to a theory of free fermions. Okay?
What happens to the interaction term? The last term is 5.
Well, once the scalar field is massive, we can just integrate it out and forget about it. Oh, sorry, yeah. Yeah, so then just forget about that term.
So they'll be free massive fermions, I guess?
No. They'll still be massless. The scalar field is the only thing that
Sure,
gets a
when
mass.
you integrate it out, why don't you get a 1 over m squared from the phi property?
You can argue based on the symmetries of the mass term for the fermions would break parity. So that wouldn't be generated. Of course, if your UV theory doesn't have the symmetry, then you have to tune something else, namely tune the mass term for the fermion such that you have a critical, you have a Cfd in the infrared. And okay, slightly more complicated example. So 3 dimensions is interesting because we can have non-trivial conformal field theories with just scalars and fermions. But of course, we can also have gauge fields. And examples are QED. So this is kinetic, the Maxwell term. So for instance, for a Yuan gauge theory, we can also have non-abelian gauge theories. So for a Yuan gauge theory, this is a kinetic term, and then we can have some complex fermions charged under this gauge field, say with unit charge. And maybe we can also add a Chern-Simons term. And it's believed that if the number of fermions is, at the very least, if the number of fermions is large enough, then in the infrared there's a conformal field theory. For a small number of fermions, it's not entirely clear, but with a large number of fermions, one can prove in the 1 over n expansion, where n is the number of fermions, that there's a conformal field theory. And one can have a similar thing for scalars, and again, same thing. Okay? And of course, these are the simplest examples, and we can construct more and more complicated examples. So using these ingredients, it's possible to construct pretty complicated theories. If we if we arrange the matter content appropriately and we tune the couplings, we can have supersymmetric theories with up to 8 supersymmetries. Yes?
You said that every time you're writing a fermion, you're not writing a mass term. Can you say that you can also prove that?
Right, because I'm assuming that I'm preserving. Right, I could add the mass term, but the mass term breaks parity. So if I don't write it, it won't be generated. And one thing I want to mention about these things, it might seem like a lot of, can construct many theories, but something that's been worked out in detail in the past few years is that there are lots of dualities between them, in particular between these classes of theories, also the theories with non-abelian gauge groups. And let me just, I think I should mention some of these dualities because they're very exciting. Dualities, and these reduce a little bit the number of distinct conformal field theories we can have. So, for instance, the n equal 1 scalar QED theory, which is described by this Lagrangian, a mu phi squared, so phi is complex, plus phi squared squared. I'm not writing the mass term, that means we have to tune it in order to reach a conformal field theory. And the claim is that this has the same IR CFT as the O2 model. So this is d mu phi I squared plus lambda phi I squared squared, where I goes from 1 to 2. So this is the O2 model. And they flow to the same conformal field theory. This was conjectured, and it was actually proven long ago by Halperin, Dasgupta, and Peskin. And are similar dualities that have been discovered more recently. For example, if we add a Chern-Simons term to this theory, so if we have d mu minus I a mu phi plus phi squared plus k equal 1 Chern-Simons term. So maybe I didn't mention that the Chern-Simons level here has to be quantized, and the way it's written is quantized in integer units. And so it's just the same theory, but we add a k equal 1 Chern-Simons term. It flows to an IR Cft. And this IR Cft is the same as the free fermion, free complex fermion. Well, this is work of, well, several people, some of them in high energy, some of them in condensed matter. So Seiberg, Witten, Senthil. Okay. What's that? If k is larger than 1? Well, I don't think. In this class of theories, there are lots of dualities. I don't remember precisely which theory is dual to which one, but there are many dualities. I don't think that the one that has k equal 2 has a simple dual description, but I might be wrong. What's that? Yes. Okay, and one thing I want to mention about the gauge theories is that, so in gauge theories, and for simplicity, I'm just talking about U1 gauge theories, but I could be talking about more general non-abelian gauge theories. There are local operators that are of two kinds. One kind is gauge invariant combinations of the matter fields. So, for example, the matter fields in the Lagrangian. So, for example, in this scalar QD theory, one operator would be phi star phi. We can have more complicated things. I don't know, like F mu nu, phi star. Well, matter fields and gauge fields. So field strength. F mu nu, phi star, d nu, box phi, or something like that. I don't know. We can write many things. Yeah. Yeah. No, it's just a free fermion. Right. The free fermion is a free complex fermion, so it's got a U1 global symmetry. And we can try to couple that U1 global symmetry to a background gauge field. And then I'd have to tell you exactly how to couple this theory to the background gauge field such that the two are equivalent. Okay, so there are two types of operators. One type is just products of the matter fields, and the other type is monopole operators. And let me mention their definition. So gauge theories in 3 dimensions have a U1 global symmetry where the conserved current for this symmetry, J mu, is the Hodge dual of the field strengths, epsilon mu nu rho, F nu rho. This current is conserved because when we act with the derivative and contract the indices, then on the right-hand side we get the Bianchi identity for the field strength, and that's automatically 0. So this is what happens for all gauge theories or U1 gauge theories in 3 dimensions. and it's special to 3 dimensions. Okay, and so there's a U1 global symmetry. T stands for topological. It's related to the topology of the gauge group, and the monopole operators are operators charged under U1T. Local operators that are charged under U1T. And their expressions, they cannot be written simply in terms of the matter fields in the Lagrangian, but it's good to know that in 3 dimensions there are these kinds of operators as well. And they play very important roles in these dualities. For instance, the free fermion over here, this theory on the left-hand side doesn't have any fermions, so where do the fermions come from? Well, the fermion here, it would be one of the monopole operators. Yeah?
So, particle capsules, I need to check out
well, in this case, so what the monopole operators do is that we can just think of them as introducing they turn on some gauge field, so some field strength. So if you insert the monopole operator at some point, then so suppose it's a monopole with charge n. So this is the U1T charge. What the monopole operator does is that if you then measure the gauge flux through a small sphere surrounding it, there are n units of flux. So this is flux I need to get my conventions right, 2 pi times n. So the integral of f over the sphere is 2 pi n. Now, what happens is that in this monopole background, they're called monopole operators because this is like a monopole background for the gauge field. In this monopole background, the matter fields have well, they behave as fermions for an odd number of flux units. The matter fields are not gauge invariant, however. But when the Chern-Simons level is k equal 1, turning on the flux of 1 unit, meaning 2 pi, is also not a gauge invariant thing to do because of the Chern-Simons term. So we have to combine that with one of the matter fields. And then we get some fermion. That's how the fermion arises. Did that sort of answer your question? So the matter fields do change the statistics in the background magnetic flux. And you have to, in order to build a gauge invariant operator, you have to combine the matter fields with this process of turning on some magnetic flux. Okay. Good. So that's what I was going to say for now about the explicit constructions of CFTs. Hopefully this was good enough motivation for studying CFTs more abstractly. And I'd like to work towards studying them using the Bootstrap. For that, there's a number of basic facts about CFTs in more than 2 dimensions that you guys should know. So Cft Basics. Now, the thing is, David Simmons-Duffin gave the TASI lectures on this a couple of years ago. He has really good notes. So I don't think it would make sense to do the same thing again. So maybe I should just mention some of the, in my understanding is that Ian also covered some of this and other people. So I'd like to go pretty quickly over this and just make a list of things that you should know and emphasize some things that are interesting about them. Okay? So what are these facts? So the first one is that the symmetry algebra is SOD plus 1 comma 1 in Euclidean signature or SOD comma 2. So this is for CFT in D dimensions. Let's just focus on Euclidean for now. The generators of this algebra are rotation generators, translation generators, special conformal generators, and dilatation. And I think the most important thing, you can just write down the commutation relations between all these things. I'd like for now to work with anti-Hermitian generators. So if I want to represent these as D plus 2 by D plus 2 matrices, they would be anti-symmetric matrices. And we can write down the commutation relations between various pairs of generators. I think the most important ones are that dilatation with P mu is P mu, and dilatation with K mu is minus K mu. Are people familiar with what these generators are? I assume so. Yes? Everyone's good? Okay, good. Good. So the reason why I wrote down those commutation relations is that, by analogy with raising and lowering operators in quantum mechanics, you can see that P mu acts as a raising operator for the eigenvalues of D, and K mu acts as a lowering operator for the eigenvalues of D. Now, that's some abstract thing. We'd like to think about theories that are conformal field theories, the theories that have the symmetry algebra, as having conserved charges. So all these things should correspond to conserved charges. So M mu nu, P mu, K mu, D, conserved charges. And now the question is, what is a conserved charge operator? One way to think about it is that it's not a local operator, it's a non-local operator, and it's supported on a codimension 1 surface, and you can use it. So for instance, if I have some operator here, O, and I want to say that it's charged under some global symmetry, and I have a charge operator Q, which is a surface operator, and I can just surround this O with that surface operator. It's a codimension 1 surface, so it can surround a point, and I can this way I can measure its charge. Okay. I think it's an interesting way of thinking about conserved charges. And in this case, I can construct the conserved charges associated with all those generators pretty easily. Another thing I should mention about this is that if we deform the shape of this surface, the answer wouldn't change. So this is a topological codimension 1 operator. Okay? So I can write down the charges associated with these generators in the following way. So Q epsilon sigma. Sigma is the surface along which this thing is supported. And it has this expression. It's an integral over sigma, area element, some vector, epsilon lambda of x, t nu lambda of x, where this is a stress tensor. So these charges are related to the stress tensor. They're integrals of the stress tensor along some codimension 1 surfaces, where this epsilon here is a vector field. I can think of it as a vector field. So in particular, epsilon is d mu if the charge that I'm talking about is p mu. Epsilon is x nu d mu minus x mu d nu if q is m mu nu. Epsilon is x mu d mu if q is the dilatation operator, and there's a similar expression for the special conformal generators for q is k mu. You can check that these charges are conserved provided that the stress tensor is conserved for the first two. So Q is conserved if d mu t mu nu is 0 for these guys. And for these other guys, conservation also requires t mu mu equals 0 for these guys. Okay? So the theory has whatever operators it has, right? And suppose it has a stress tensor, and from that stress tensor we can construct these conserved charges. It's one of the space-time indices. So for instance, I would say that in this case, epsilon lambda is delta mu lambda. This is just a vector field notation for epsilon. Okay? And this way of thinking about conserved charges may not be very familiar. But actually, one nice thing about it, and there's been some work on this in the past few years, that this notion of conserved charge can be generalized so this is a codimension 1 operator, but it can be generalized to any codimension operator. Okay, so this idea can be generalized to codimension n conserved charges. So this corresponds to generalized global symmetries, where the charge objects are not local operators, but they could be line operators or surface operators and so on. And to measure the charge, we just have to surround them with a charge operator of the appropriate codimension. Okay? I'm not going to explain that, but I thought I should mention it. And now, if we have, we'd like to define a notion of these conserved charges as acting on the operators in the theory. Okay? So if I have an operator inserted at x, suppose the operator is O of x, we can define the charge Q. So define the charge Q acting on the operator O So this is, we're going to get another local operator. The way this is defined is as a limit when the radius goes to 0 of q sigma r centered at x O. So I take my operator O, and I surround it with this conserved charge operator, and then I take the limit when the radius of this small sphere goes to 0. And this is a way of defining a new, so this is a new local operator. So the conserved charges act on the local operators and give us back local operators. So the local operators transform in representations of the symmetry algebra. Yeah.
This Euclidean setting.
Euclidean setting.
Sorry, Euclidean setting. Conservation is equivalent to this being topological.
Exactly. Conservation is equivalent to this operator being topological. So if the theory has global symmetries, it has some topological, codimension 1 topological operators that can be used to measure the various charges. Okay? David Simmons-Duffin explains this in detail in his notes. This is roughly the idea. And then these conserved charges can be, since they act on the space of local operators and give us back local operators, so local operators transforming representations of the symmetry algebra, we can try to think about what those representations look like. So the way to do that is first to start with x equals 0, operators inserted at the origin. What's nice about x equals 0 is that this is a fixed point of rotations and dilatations. And rotations, I didn't write the full algebra, but rotations commute with dilatations, roughly because the dilatation operator is a scalar. So it can transform under rotations. So we can choose a basis of operators. O of 0 that diagonalizes D and M mu nu. Since they commute, they're simultaneously diagonalizable. So what it means is that D acting on the operator at 0 is some eigenvalue times the operator at 0. And M mu nu acting on the operator at 0 is some eigenvalues, but it's better to think about it. Instead of actually diagonalizing mu, we can just turn it into a block diagonal matrix. So the blocks, I can label them like this: S mu nu A B O B. Well, maybe if I want to follow David's convention, I can just do that and put an index A on these operators. So these operators transform in some representations of the rotation group. These are, so that's why they have an index. The index run from 1 to the dimension of that representation. This is just a set of numbers that corresponds to these matrices M mu nu in that representation. Okay? Yeah?
When you say diagonalize, do you mean in the space of all local operators?
Inserted at the origin, yeah.
Okay.
Yeah. You know, acting with conserved charges takes local operators to local operators, so we can first think about the origin. And then we can think about what happens if we act with k mu and p mu, and as I said before, p mu raises the eigenvalue of D by 1, and k mu lowers it by 1. So then we have this picture of well, we can have this as a possible representation of this conformal group. They're called lowest weight representations, irreducible representations, where we start with some operator O inserted at the origin. Let's say we call it O0. And then we act with, it has some scaling dimension, so this is scaling dimension, or the eigenvalue of D, delta. And then we act on it with P mu. We get some operator O1. We act with it with P mu. We act on it with P mu again. We get O2, and so on. And this goes on forever. And to go back, so this after we act with P mu once, the scaling dimension would be delta plus 1. Twice would be delta plus 2, and so on. And to go back, we act with K mu. So it must be that if we act with K mu on the lowest one, we get 0. Okay. And this implies the notion of a conformal primary. So this is the conformal primary. So the conformal primary operators are the local operators with well-defined scaling dimensions, transforming in a well-defined representation of the rotation group, such that when put at the origin are annihilated by K mu. Okay. Conformal primary. And these guys that are obtained by acting with P mu are called descendants. Questions about this? This was operators at the origin. Operators away from the origin. We can figure out how those are acted on by all these conformal charges if we wanted. I think it's good to write down how they're acted on by D. So as I said before, so D when acting on an operator at the origin gives delta times that operator. But question, what does D do when acting on an operator at X? Well, we can just do the calculation. First of all, what is an operator at X? Here we had just operators at the origin so far. An operator at X, I can define it by saying that this is e to the x dot p acting on the operator at the origin. P is the translation operator. And in this language of surface operators, this is how we translate by x. Yeah.
Just a question.
Good. Let me try to explain that. If you think about the action of operators of these conserved charges as I defined it, where you surround the operator by some codimension 1 operator, then you don't have to conjugate it. But, so suppose I have some operator O here, and I'm surrounding it by a conserved charge operator Q. Since the conserved charge operator is topological, I can deform this surface any way I want. And I get the same answer. So in particular, I can deform it to be of this type, O of 0, and to look like that. And this, so suppose that, for instance, the time direction runs like this, T. Okay? And this can be interpreted as, now you see this conserved charge operator acts at a given time. So I can interpret this as, because of the different orientations of the surface, this one's oriented this way, this one's oriented that way, I can interpret this as Q times O minus O times Q. So this would be the commutator between Q and O. Yes, this would be inside a correlator where there's time ordering. Okay? So, if you define this surface to be two parallel planes, you can have this Q acting on the operator as, you can write it as Q at some time times O minus Q at some other time times O. Same thing with position. And then when you exponentiate it, you're going to get e to the x times p on the left and e to the minus x dot p on the right. So the difference is just what kind of surface operator I'm surrounding my local operator with. If I surround it with spheres, then the action is defined as before. If I think of this as being one plane at some x and some other plane as minus x, then it would be e to the x dot p, O of 0, e to the minus x dot p. Yeah?
Are you using the representation of p where it's just a derivative?
Yeah.
Same reason that it's not commutator, dO equals delta of O, it's just d times O.
Right. But with this, in a certain quantization of the theory, you can interpret this as a commutator.
So I guess surrounding by a sphere and when surrounding by like two planes, and that's interpreted as a commutator.
Once you quantize the theory, yes. Because these operators are topological, so I can turn a sphere into two planes. Okay. So then, I could just figure out what d of O of x is. So this is d e to the p dot x, O of 0. And then I can write this as e to the p dot x, e to the minus p dot x, d e to the p dot x, O of 0. Now I can think of these things here as elements of, I can think of p and d as Lie algebra elements. So then, to evaluate this quantity, we can use the Baker-Campbell-Hausdorff formula. So this is BCH. This gives d plus commutator d with p dot x. So this is the same as d plus x mu p mu. And p mu acts as a derivative. So, and this thing here translates it to x back to x. When you think about this, you get that d acting on O of x is equal to delta plus x mu d mu O of x. The point that I'm trying to make is that this follows from a simple application of the Baker-Campbell-Hausdorff formula. And similarly, we can figure out what mu nu is when acting on an operator at x, and what k mu is when acting on an operator at x, and so on. Okay? So now, since we've done this, the next thing to know is how the correlation functions behave. How they're restricted by the symmetry. And I assume people know this. So, correlation functions. So let's just talk about correlation functions of scalar primaries. Let's say OI with dimension delta I. The simplest thing is one-point functions, the one-point function of an operator O is 0 unless O is the identity operator. Two-point functions, O1 at x1, O2 at x2. By rotational invariance, this is just a function of x1 minus x2. But since the theory has all these symmetries, it should be invariant. That function should be invariant under the action of D on both operators. So then we can just write down, there's a differential equation, delta 1 plus x mu d mu, delta 1 plus x1 mu d1 mu plus delta 2 x2 mu d2 mu acting on this thing should be 0. So that implies that the fact that it's invariant under dilatations. Okay, so let me write like this. So this is f of x1 minus x2. The fact that D acting on this is 0 implies that f is 1 over x1 minus x2 to the power delta 1 plus delta 2. So that's just using dilatation symmetry. If we now further require that this correlation function is invariant under special conformal transformations, so k mu acting on this is 0, this implies that the two-point function O1 of x1, O2 of x2 is 0 if delta 1 is not equal to delta 2. So choose a basis of operators such that so the only non-zero two-point functions are between operators with the same scaling dimension, and we can choose these operators such that OI of x1, OJ of x2 is delta ij over x1 minus x2. Here f is a constant over this. We can choose the constant to be 1 by normalizing the operators. So this would be 2 delta I. Yeah?
Sorry, I had some questions about this.
Yes?
So I'm going to measure my O at one point, and I'm going to get 0 on average. But I'm going to measure that 0 with infinite variance of what xi equals x, sorry, x1 equals x2. I just want to measure operator x1, period. And I get 0 on average. And now I want to know what the variance of my measurements are. I do square, I get infinite variance. How does that make sense physically? I mean, that's true in other theories.
Well, right. That's a thing about quantum field theory.
Okay.
They're large fluctuations. To get larger and larger as you put the operators closer and closer together. Well, I mean, you can see it from from these formulas. What's the physical reason for that? What's that? Yeah, but that doesn't imply that it should be infinite. The question is about whether it's infinite versus finite. In quantum field theory, there are large fluctuations.
I mean, I guess you can just say, like, a measurement apparatus, but the finite, I can never actually measure an x1. Or, sorry, yeah.
Well, I mean, it all has to do eventually with the uncertainty principle, I suppose. we can, but you can redefine. So suppose we have some operators such that the matrix of 2-point functions is not diagonal as I wrote it. Then we can just diagonalize it. So that would be a convenient way of finding a basis. Okay. Just to give you an idea of what this looks like for operators with spin. So this was for scalar operators. For operators with spin, we have O mu1 through mu L at x1. Let's just take one of them at x and the other one at 0. O mu1, let's say, sorry, nu1 through nu L at 0. So, the form of the 2-point function was fixed by of scalars was fixed by conformal invariance to this simple thing. For operators with spin, it's also fixed, but to a much more complicated thing. Okay, so this is a constant that depends on the operator times something that takes care of these indices, and I'll write this as I mu1 nu1 at x, I mu2 nu2 at x, and so on, I mu L nu L, divided by, if the operator has dimension delta, then this would be x to the power 2 delta, where, well, it's not quite complete. So what does it mean to have operators with spin, first of all? Well, they have several Lorentz indices that are symmetrized, and the traces are removed, because if we contract 2 of them, we can get an operator with a lower spin. Okay? So these operators are symmetric and traceless in these indices. In order, on the right-hand side, to have something that's symmetric and traceless, well, we should just symmetrize, say, the mu's and remove the traces. So this would be the formula. And now I have to tell you what I mu nu is. At x is delta mu nu minus x mu x nu divided by x squared. Yes?
Should we really say that this V acting on the equilibrium for 0, we're looking at trace V that equals that plus
delta functions sometimes are possible. I'm just thinking about correlation function at separated points. Okay. So that's 2-point functions. The next thing is 3-point functions. So I'll just write down the formula so that people have it in their minds. I'm not going to derive it. Yes? In 3 dimensions, this is all there is? Yeah. There could also be spinor representations, but I'm not talking about spinors yet. Okay. 3-point functions. So they look like this. O1 at x1, O2 at x2, O3 at x3. This is some constant, f123, divided by x12 to the power delta 1 plus delta 2 minus delta 3, x23 to the power delta 2 plus delta 3 minus delta 1, x13 to the power delta 1 plus delta 3 minus delta 2, where xij is xi minus xj. Okay. I assume people have seen this formula before. So the 3-point functions are determined only up to this overall constant. For operators with spin, of course, it's more complicated because if these operators have indices, then we have to have here some function that depends on those indices and the x's, like for the 2-point function. I'm not going to write down the formula. It gets pretty complicated very easily. 4-point functions. And this is actually going to be important. Well, all of this was important. Now suppose we have a 4-point function 01 through 04. So if you work out the constraints that follow from conformal invariance, get that this is, well, so let me assume for now that delta 1 is delta 2, delta 3, delta 4 is equal to delta. So the operators have the same scaling dimensions. Otherwise, the formulas are going to get more complicated. So this is 1 over x12 to the 2 delta, x34 to the 2 delta, times some function g of two variables u and v that are related to x1 through x4 in the following way. U is defined as x12 squared, x34 squared, divided by x13 squared, x24 squared, and v is x14 squared, x23 squared, over x13 squared, x24 squared. These ratios are invariant under conformal transformations, under all conformal transformations. Okay? That is the 4-point function. One important property of this 4-point function is, or the set of all 4-point functions, is crossing. So let me write that. So let me write it, it's simplest to write it for identical operators. Otherwise it gets more complicated. So let's assume that 01 and 04 through 04 are the same, and they're called O. So then I can write this 4-point function in several ways. So I can write like this: OX1 through O of x4 is, as I wrote it above, 1 over x12 to the 2 delta, x34 to the 2 delta times g of uv. But since the operators are the same, x1 through x4 are just labels. These are Euclidean correlators. You can always interchange the order of the operators and rename x1 through x4. So I can, for instance, rename 1 to 3, x1 to x3, and x3 to x1. And if we do that, we get what? We get 1 over, so x1 is x3 and x3 is x1. So here we get x23 to the 2 delta, x14 to the 2 delta, times some function. Well, it's the same function, but evaluated at a different point, that's obtained by renaming, by interchanging x1 and x3. So what happens if we interchange x1 and x3? The denominators stay unchanged. And in the numerator, if I replace this with 3, and I replace this with 1, I get exactly the other one. Right? So under x1 goes to x3, u and v get interchanged. So it's this times g evaluated at v comma u. Of course, the interchange 1, 3 is not the only one I can do. I can also interchange 1 and 4, for instance. Let me try to figure out. just one second. Right, we can interchange 1 and 4. We can interchange, any pair. It turns out that you can generate all possible interchanges from just 2 of them, interchanging 1 and 3 and interchanging 1 and 2. So let me write this again, where we interchange 1 and 2. If we interchange 1 and 2, the power up front stays unchanged. So x12 to the 2 delta, x34 to the 2 delta. But interchanging 1 and 2 actually changes u and v. It doesn't change the numerator of u, but it changes the denominator. It also changes this denominator. It also changes the numerator over there. You can work out what that does. So interchanging 1 and 2 is the same as sending u to u over v and sending v to 1 over v. So this is the same 4-point function as 1 over x12 to the 2 delta, 1 over x34 to the 2 delta, times g evaluated at u over v 1 over, and 1 over v. Is this clear? The reason why I consider the same operator is that under these interchanges, the interchanges map the 4-point function to itself. If we had different operators, these interchanges would map this 4-point function to a different 4-point function. But if we consider the set of all 4-point functions, they get mapped to the same set. Okay? So for identical operators, g of u of v must be the same as g of u over v and 1 over v, and g of u of v. So this is just setting this one equal to that one. Interpreting this relation is a little more complicated because we have to bring, so for instance, we bring this x23, x14 to the left-hand side. And if you look at what this can be written in terms of u and v. If you work through the algebra, you get that g of u v is u over v to the delta times g of vu. Where this u over v to the delta just comes from the fact that the prefactors are different. Okay? Questions?
Can I completely specify a CFT with all the 3-point function information? Every single one. All the
yes, but well, that's sorry. The answer is no, for 2 reasons. One reason is that specifying the OP coefficients may not be consistent with other principles like unitarity that I was going to mention now. Okay, so there's consistency conditions that one has to take into account. And second is that this only gives us information about the local operators. The theories might also have non-local operators, and there might be additional data associated with those operators. I'm not sure about 2D, but certainly in 3D because, Chern-Simons theory is an example of a CFT that doesn't have any local operators, but has non-local operators. So clearly specifying all the OP coefficients in that case doesn't specify the theory. Okay? So, okay, another thing, working towards the Bootstrap, unitarity constraints. So far I've been talking about Euclidean theories. So if you have here Euclidean, you can continue this theory to Lorentzian signature. But in order to do so, we have to specify which direction is time. So suppose that time goes in this direction. So the time slices are like this. Now, when we quantize the theory, we associate a Hilbert space with each of these time slices. And the operator that takes us from one time slice to the next is the time evolution operator, which is e to the minus I h Lorentzian t Lorentzian. And indeed, O of, in Lorentzian signature, O of t and x, maybe I can just write it on the next board. I guess one thing that might be confusing about this is that it all depends on which direction is time. And it really does. I mean, if we take time to go in a different direction, it could be a completely different Hilbert space. Okay? So Hilbert space that we're talking about depends on which direction we call time. And the operator of t and x is e to the I h l t Lorentzian O of 0 and x, e to the minus I h Lorentzian t Lorentzian, where hl is a Hermitian operator. So in order to go from Lorentzian, so this is t Lorentzian, in order to go from Lorentzian to Euclidean, we just insert an I. So t Lorentzian, we set t Lorentzian as minus I times t Euclidean. And in Lorentzian signature, operators are that act on the Hilbert space. Operators associated with observables are Hermitian operators. So O dagger is O, okay, at the same time and x. However, if we try to write this in terms of the Euclidean time, we get e to the h Lorentzian te. Just plug in that formula. TL is minus I te. O of 0 and x. E to the minus h Lorentzian times te. So then the condition, the Hermiticity condition, so O of t Lorentzian x dagger is equal to O of t Lorentzian x, in Euclidean signature becomes O of t Euclidean and x is conjugate is O of minus t Euclidean and x. So while in Lorentzian signature, conjugation relates operators at the same time to each other, in Lorentzian signature, this happens in Lorentzian signature, in Euclidean signature, conjugation, the same conjugation, the one from Lorentzian signature, the same conjugation relates the operators of te to the operators minus te. And this relation depends on which conjugation we're talking about. So this conjugation I'm talking about here is associated with this particular direction as being interpreted as time. If I were to interpret a different direction as time, this relation in Euclidean signature would change. Okay? So this conjugation is just some action on the space of all operators that relates operators at some point to the operators at some other point. Okay? And in particular, what this implies, for instance, is a property called reflection positivity for Euclidean correlators. And that's related to unitarity in Lorentzian signature in this way. And so that property is that O of minus TE and X, O of TE and X this 2-point function, because of this conjugation property, this is the same as a norm of O, T, E, and X acting on the vacuum squared, so this should be positive. So correlation functions that are, for instance, 2-point functions, but generalizes to higher point functions that are reflection symmetric about some plane, the direction perpendicular to that plane is interpreted as a time direction. So all correlation functions that are symmetric, where the operators are symmetric, have to be positive. That's a consequence of unitarity from Lorentzian signature. Okay? So in particular, when I wrote down the form of the 2-point function being this implies that C is bigger than 0. And of course, for these operators with spin, it's a little more complicated. But we can take the Lorentz indices to be in the directions perpendicular, perpendicular to the time axis. And then one can derive a positivity condition for CO as well. Okay? Yes? Yeah, I believe that's true. Yes, in the continuum case, yes. I think if you have lattice models, the situation could be different. However, this is not the only conjugation that's useful. There's another conjugation that comes from radial quantization. Where, the way to think about it is this. So you start with your flat space. This space, the metric on this space is dr squared plus r squared, the metric on S2. This is related, I can write this as e to the, if I make it the definition, r is e to the tau. I can write this as e to the 2 tau times d tau squared plus d S2 squared. So this space is related up to an overall scale factor to a cylinder. So it's related to something like this, where the base of the cylinder is a 2-sphere, and this direction is parameterized by tau. And it's possible to continue this direction, this tau direction, to Lorentzian signature and interpret this as a time direction. And that imposes different conjugation relation. Okay, so send tau to Lorentzian time. And what that does is that it implies the following relation for scalars. And I'll stop here with this. So O of x conjugate is 1 over x to the 2 delta times O evaluated x over x squared. So this is the unitarity implies this relation. So again, in Euclidean signature, the conjugation relates operator some point with operator some other point. In this case, the relations seems pretty complicated. Here I wrote the operators in flat space. So I can think of mapping the flat space to the cylinder. Then I interpret this time direction as the Euclidean time direction. I continue it to Lorentzian time. I impose the unitarity condition. In that setting, unitarity relates operators at some point to operators at the same point. And then I continue it back to Euclidean signature and try to see what it implies about the operators in flat space, and this is the condition that it implies. Okay, so it relates the operator at x to an operator at x over x squared. I suppose I'm probably supposed to stop soon. Just about now. So I will continue this afternoon.
Yeah, so for the first activation, we will still have operator state.
Have an operator state correspondence. Well, I believe I can think of, yeah, I believe so. I believe I can think of acting with some operator as generating or changing the state on one of these slices. Where did I use conformal symmetry? I don't think I used conformal symmetry. Well, I mean, certainly I can foliate this space with slices, and on each slice there's a Hilbert space, so the Hilbert space has states, and then I can try to think about what happens if I act with the operators on that Hilbert space. So suppose I take an operator and act on the vacuum, it definitely creates a state. Perhaps the other way may not work. I'm not sure. Right, the state that if I start with a state, the question is a local operator related to a state or not? And I think that's probably false. But what's true is that if I allow myself to not just talk about local operators, I also talk about non-local operators, then they are probably related to states. I can think, if I start with an arbitrary state, I can think about an operator that would create that state when acting on the vacuum. It would be a non-local operator. You mean it's not? Right, if I want to talk about normalizable states, then for sure I have to think about non-local operators, because with a local operator I create a non-normalizable state in this way of quantizing the theory. Right. So for local operators, I don't think there's a state operator correspondence. What's interesting about this one is that local operators will correspond to states.
How much is known about
Not so much, even though there are a few papers about this. Yeah, I can, if we have two line operators, for instance, these surface operators are more complicated. They're also more boring because they're topological, but suppose we have line operators. Then you can construct OPs and things like that. But in that case, I don't think that the two-point function, well, I'm not sure. I think the positivity conditions are not, the positivity conditions that are needed for the bootstrap may not be there. But maybe it's just my ignorance about the subject.
One more question?
Yeah. Either one. Yeah, I think they are equivalent.
So if you can bring it back to unitary symmetry on the sphere, then it also has this unitary on.
Yeah, I believe so, but I don't have the argument in mind now. I believe that's true. People aren't talking about two different notions of unitarity. It's like the answer is more like, you know, from a sociological point of view, someone would have told me if there are two different notions of unitarity. So I believe it's the same, but I need to think about it.
Okay, so let's take a coffee break.
On like that. And it works automatically.
And it works automatically.